In this video, or rather in this video series, I will focus on one of the major application areas of quantum computers: simulating nature. Now, nature here is meant in a very broad sense, and what I really mean is the fundamental processes that unfold on the atomic and molecular scale. Traditionally, we simulate these processes using the physical laws we know from physics, translated into mathematics, and then run those mathematical models on powerful classical supercomputers. The idea behind quantum computers, however, is very different. Instead of relying purely on mathematics to approximate quantum effects, we build devices that are intrinsically governed by the laws of quantum mechanics themselves. In other words, we no longer need to simulate quantum effects through mathematics alone. We directly harness these quantum effects and properties as the resource to perform the computations. First, I'd like to give you a quick overview of what I'll be covering in this video as well as in the upcoming ones. I'll begin with the motivation, why we even want to simulate nature in this way and why classical computers are no longer sufficient for this task. In the second step, I'll present a concrete example from material science. I'll sketch out what a typical workflow looks like today when researchers want to develop a new material and how that process unfolds from start to finish. As the third point, I'll highlight the different application areas of simulating nature with quantum computers. For instance, as already mentioned in material science, but also in other domains. In the fourth step, I'll dive deeper into the example from step 2. I won't go into extreme detail, but I'll provide a more mathematical and structured picture so you get a clearer sense of what is actually being done in such simulations. The fifth point will then focus on the bottlenecks of the classical approach. Some of this will already become visible in step 4, but I'll take a closer look here at where the real limitations lie. The goal is to make it crystal clear why quantum computers could be incredibly valuable when it comes to simulating nature. In the sixth step, I'll show how quantum algorithms can address this challenge. As an example, I'll walk through how to calculate the ground state of an H2 molecule, not classically with supercomputers, but using a quantum computer. And finally, in the last step, I'll demonstrate all of this in practice using Qiskit. With a hands-on code example, I'll show that this approach really works and that on a small scale, for something as simple as the H2 molecule, it can already be implemented today. Let me begin with a motivation. To explain why we want to simulate nature with quantum computers in the first place, and why this approach offers advantages compared to simply running calculations on classical computers using mathematics alone. Over the past century, physics has given us a remarkably clear picture of how the universe works at its most fundamental level. Regardless of how we interpret it or how we think it really works, quantum mechanics itself, the framework we developed to describe the universe at its core, is astonishingly successful. In fact, it is the most precise scientific theory we have, with predictions that are more accurate than any other theory in science. Now, the way we usually proceed is this. We take the physical laws we have discovered, express them in mathematical form, and then apply those mathematical relationships to make predictions. Mathematics serves as our tool, allowing us to work with these laws in a practical way. For example, we can use mathematics to predict how certain materials will behave, their electrical conductivity, their hardness, how easily they might break, or at what temperature they will melt. We have our physical laws and formulas, and through mathematics we can calculate many things. And these calculations, however, are far too large and complex to do by hand, which is why we rely on computers. But even ordinary computers are quickly overwhelmed. For many of these problems, we already need supercomputers. With physics, mathematics, and the power of supercomputers, we can indeed describe nature's behavior quite well. But here's the critical point. Supercomputers themselves eventually hit a limit. For more complex systems, even their enormous computational power is no longer sufficient to carry out the calculations. The challenge we face is the following. In quantum mechanics, let's consider a particle. The This particle can exist in, say, X different states. It doesn't matter what those states look like in detail, the point is that there are X of them. To simplify, you could imagine just two states, like an electron that can be spin up or spin down. But to keep it general, let's say our quantum object can occupy X possible states. Now the moment we add a second particle, the entire system no longer has X states, it has X squared. With 3 particles, it becomes X cubed, and so on. In general, a system of n particles spans X to the power of n possible states. And here's the core difficulty. In quantum mechanics, all of these X to the power of n states exist simultaneously in superposition. That's what makes the problem so hard. These states also interact with one another, producing constructive and destructive interference. As a result, the probability of measuring the system in a particular state is shifted up or down, depending on how the states reinforce or cancel each other out. Some states get amplified, while others are suppressed, and in the end, we're left with a distribution of probabilities across all possible outcomes. The challenge then is that with classical mathematics and conventional computers, we are forced to simulate every single one of these states and account for how each one influences all the others. This number grows exponentially, and the calculations soon become unmanageable. Very quickly, the problem surpasses what even the most powerful supercomputers can handle. The alternative is to build a device, a quantum computer, where we don't have to simulate each state individually. Instead, we construct a system that directly embodies the same conditions as the quantum system we want to study. The qubits in the machine naturally enter superposition, they can become entangled, and they interfere with one another. All of those effects that we previously had to calculate one by one happen automatically within the quantum computer. So what's left for us is not to calculate each possible state explicitly, but rather to design and build a quantum computer capable of representing the system we care about. As an analogy, imagine throwing a stone into water. A wave ripples outward across the surface. With physics, we can describe this in detail. The stone falls from a certain height, hits the surface at a certain speed, has a given mass, and so the wave propagates with a specific velocity, period, and amplitude. Now suppose we throw a second stone into the water. Another wave forms and the two waves overlap. They interfere and combine into a new shared wave pattern. In principle, we could calculate this entire process by hand. If we drop the stones from these heights with these speeds, here is what the resulting wave pattern will be. Or, instead, we could simply go to a pond, drop the stones, and watch the waves emerge naturally. And the second approach, where we don't just calculate the outcome but actually let it happen, that's much closer to what we do with a quantum computer. And this brings us to a crucial point. A quantum computer does not operate like a classical computer. Instead, it is a fundamentally different kind of device. In essence, a simulator of nature at the smallest scales. It's not the same as performing a physical experiment on nature directly, but it's also not a mere abstract calculation. It's an engineered system designed to reproduce quantum behavior in a controlled way. A classical computer simply doesn't have the power to carry this out once the complexity grows too large. So we build a new kind of machine, one that operates according to quantum mechanical principles and, in that sense, simulates physics directly at the quantum level. This idea goes back to Richard Feynman, who first suggested that if we want to understand quantum systems, we should build machines that use quantum mechanics themselves. That was the spark for the very concept of quantum computing. Now, having said that, I hope I've provided a clear motivation for why quantum computers could be very useful. In the next part, I go into more detail about how today's process of developing new materials actually works, and I show exactly where and why the bottleneck arises. I'd also like to give a brief example of what such a process might look like. This won't be very detailed. I'm not a material scientist myself, but it should give you a rough sense of the overall workflow. First, we start with a problem statement. For example, let's say we want to discover a new material. A common goal you might have heard of is finding a room temperature superconductor. But of course, we don't just want it to be superconducting at room temperature. It also has to be practical to produce. Maybe we want to manufacture wires from it, so it can't be too exotic or fragile. And it also has to be affordable. We're not looking for some extremely rare material that barely exists on Earth. So our problem is clear. Find a superconducting material that works at room temperature, is easy to make, and is reasonably cheap. The first step is usually a screening process. Here, the goal is to narrow down the vast number of possible candidates. This is done partly by relying on the experience of material scientists, but today increasingly also with the help of machine learning, which is very good at spotting useful patterns. Using this, we can generate a list of promising candidates, different combinations of elements arranged in different crystal structures. There are an enormous number of parameters that can vary, leading to very different properties. At the end of this screening, we might reduce the search space down to several thousand candidate materials. The next step is to move into simulation. At this stage, a widely used method is density functional theory, or DFT for short. The aim of these simulations is to calculate the so-called ground state energy and the corresponding ground state wave function of the material. So what do we actually need these two quantities for? With the ground state wave function and the ground state energy, we can already do a lot. For one, they tell us whether the material can exist in the first place. And directly from the ground state energy and the wave function, we can compute additional properties. For example, binding energies, reaction enthalpies, or the electron density. In other words, once we have these, we can build on them to derive further quantities, many of which can still be computed classically without a quantum computer. If, on the other hand, we want to know more, say optical properties, for example, then we can't stop at the ground state. We also need the excited states. That means running the algorithm again, this time targeting excited states rather than the ground state. This detail isn't crucial right now, but what matters is that these two pieces, ground state energy and ground state wave function, are the first essential step. From them we can compute the parameters that tell us whether a candidate material is promising or not. We have to do these calculations for thousands of candidates. From that large set, if a few candidates produce good parameters and look promising, we can then move to the lab. Try to synthesize them and see whether their real behavior matches what the simulations suggested. The problem, however, is precisely these simulations. They must be run on supercomputers and are extremely compute intensive. Even evaluating a single candidate from those thousands can be very demanding, and running this across thousands can take days or weeks, depending on the size of the supercomputer available. And it is, of course, expensive. This is exactly where quantum computers would step in. They would replace this simulation stage and accelerate it by a large factor. That, in a nutshell, is the workflow. Next, I'll outline the application areas where quantum computers can be used in simulating nature, and after that I come back to the mathematical side of the calculation. I won't go into every last detail, but I walk through it at a general level so you get a clear sense of why these simulations are so computationally intensive. So now, as mentioned, let's look at the applications. The areas where simulating nature with quantum computers could really make a difference. Of course, there may be others that I won't cover here, but these are the core fields, I think. The first area is material science. As I explained earlier, calculating molecular configurations is extremely demanding, but by doing so we can discover new materials for specific purposes. For example, better batteries or room temperature superconductors. The second area is fundamental physics. This includes things like quantum field theory or many-body theory, which are often interactable with classical methods. Quantum computers could in principle help us tackle these kinds of problems. However, in this area, we would need a very large and advanced quantum computer, so these applications are likely further down the road. The third area is climate and environmental science. Today's climate models, which run on supercomputers, rely heavily on approximations of how molecules in the atmosphere behave. That behavior is inherently quantum mechanical, but because of the computational limits, we have to use approximations to make the models tractable. With quantum computers, we could calculate molecular interactions in the atmosphere more precisely and thus make better predictions about climate dynamics. The fourth area is chemistry and industry. Many chemical reactions involve strongly correlated systems, which are very difficult to simulate classically without approximations. Quantum computers would allow exact simulations of molecules and reaction pathways, enabling us to discover new catalysts for industrial processes. And while this isn't strictly quantum nature, quantum computers could also optimize complex workflows in logistics, production, or energy distribution. And the fifth area is biology and life sciences, which is another very exciting field. Biomolecules, proteins, DNA, enzymes are enormous and extremely complex. Their behavior is rooted in quantum effects, and quantum computers could help us simulate them in unprecedented detail. For example, we could simulate protein folding, better understand enzyme reactions, and even carry out more accurate drug design, computing the exact binding between a drug molecule and its target, which today can only be approximated. In short, the key takeaway is this: any field where progress depends on simulating molecules to understand their behavior, whether that's designing new medicines, creating new materials, advancing fundamental physics, modeling the climate, or improving industrial processes, is a field where quantum computers could be transformative. They wouldn't just make these simulations faster, but also qualitatively more accurate. And that brings us to the end of this video, part 1 of this series. I've kept this part more general, so it's accessible to as many people as possible. In the next video, things will get a bit more technical and mathematical. I sketch the workflow in more detail, highlight the step that becomes computationally so demanding, and show a concrete example from a study that calculated how long such a simulation actually takes. It will be a little more in-depth, but I've still tried to keep it understandable, even if you're not a physicist or a mathematician. I hope you tune in again. See you next time.